needs to adapt to climate change, but at the same time is a very high contributor to climate change. And even though if we reduce all those greenhouse gas emissions, even if we would reduce them to zero, you would still see climate change happening because it's such a long-term process. It's not by shutting down the emissions today that we will prevent climate change. We will still see effects. So our urban environments need to both focus on mitigating climate change as well as adapting to climate change. An interesting phenomena that we have is the urban heat island. I don't know who is familiar with what an urban heat island is. Someone?
It's the phenomenon where cities tend to be 2 to 3 degrees warmer than the natural pulse around it because of all the hot surfaces that reflect, radiate, which is not typically what you find actually.
Yeah.
Runoff instead of groundwater penetration.
Yeah. I'll add some additional things. It's indeed the general concept what you say is when we see the temperature differences between urban and suburban areas. Heat that gets trapped, as you correctly mentioned. There's also the heat that we expose in our cities also playing their roles, of course. If we would fill up a city with those air conditioning units, then they get out the heat in our buildings, but they just put it in our outer environment. Something to reflect upon if you would install full air conditioning on buildings in those external units. There's one more thing I would like to add to your explanation of the urban heat island, and that is that the difference is actually something that you mostly see during the night. And if you look here, so it's a conceptual figure of an urban heat island. So they made a section throughout a city where you have some rural area, you have a bit more suburban area, you have a park in between, then we come into the city core, and then again we have some rural area. In black, you see the surface temperature during the day, during the night, and in red, you see the air temperature. And during the day, you see that the surface temperature differs quite a lot throughout this section, but that actually the air temperature does not differ that much. There are of course some smaller variation, but in air temperature it's not exactly that much warmer in the center of the city as it is in a rural area. That's air temperature. Of course, if you're standing next to a concrete building, then that surface temperature might rise up to 50, 60 degrees. That will feel way warmer than if you would stand in a rural area in the middle of nowhere, of course. But in air temperature, differences are not that big. Well, if you look at night temperatures, it's a completely different story, and it has to do with what you indeed say. During the day, we have the heat that gets trapped, and during the night, all the heat that gets trapped into the city is released again, and makes that you have way higher temperatures in the city center during the night than what you see in rural areas. You also see a slight effect of how wind might impact that. So we see slightly lower temperatures at this side of the city in this section than what you would see on the other side of the city. So that also plays a role. So if you look at an urban heat island, you see here multiple urban heat islands for different cities across the world. Mind the spatial resolution of those cities, so it's from a smaller city to a way bigger city, and you see very different forms of urban heat islands related to the layout of the city, but also in how, for example, for Canada we see also a river, how that might affect, so that is playing its role. Wind, as I said, also has an important difference. Here you see twice an urban heat island mapped for the city of London, but with calm wind conditions and with a wind of 3 meters per second. Where you see in calm conditions we have an urban heat island with a difference even up to 8 degrees during the night. If the wind speed is way higher, so if you get a good flushing actually of the city, it's reduced to 2 degrees Celsius. Of course, for that flushing of your city, the layout of your city also is an important one. So if you have large building blocks, but they are frontal on your wind direction, then the wind can of course not go through and it will reduce the flushing possibility. Well, if you adapt your building layout in your city and to accommodate actually the most prevalent wind directions, it will help to reduce those temperatures during the night. Of course, that might be a possibility if you start from scratch. In most cities, we have the plan we have to work with, and we have to look for possibilities to improve or to reduce worse conditions, but it's of course a completely different story to take into account. As I said, urban heat island plays its role in climate change. So you see here why cities are a hotspot of global warming. So the city geometry can increase locally the effect on temperatures with 1 degree additional warming in that city, even up to 2 degrees. Depends a bit on the uncertainty of what is taken into account. Human activity within those urban areas could also increase to around 1 degree temperature. Building properties will have their impact. Well, if we have water bodies included, if we have vegetation included, then that might have actually the urban cool island effect, so that will reduce local temperatures. Urban climate change, how the impact might look like. In the next set of slides, I would like to dive deeper a bit more in how are those models working. What could be of interest in what you're doing, and also to give you a bit of a background, to be aware if you get future climate data, whether it is in a 2D graph, whether it's a CFD simulation for a certain area, whether it's a weather file as the ones you've worked with in previous module, what to be aware of if you use the data and what might be playing its role in how you interpret it, the impacts. The basics of climate models start with a general circulation model on global level, which comes down to putting a 3D grid across the globe. So you actually get those grid boxes, as you see here on the right-hand side. You have those grid boxes from the Earth's surface to high in the atmosphere. You also have certain grid boxes below ground to also incorporate processes going on. And what is actually the purpose is that within each grid box, you solve a whole set of equations representing all physical processes ongoing. There are a lot of processes, something I should not explain you anymore, which also makes, if you do this on a global level, then such a grid box has a size of about 200 kilometers by 200 kilometers to still make it computationally feasible to calculate. The computers that they use for those kind of models kind of look like this. It's not your laptop that is able of calculating such a thing, so it's a quite extensive models demanding a lot of infrastructure, computational infrastructure to do so. Of course, if we have a grid cell of 200 by 200 kilometers, that does not say, or that does not give us the necessary information of what would happen to that one city in the middle of a 200 by 200 grid cell. So that's why we need to increase the resolution of those grid cells to be able to see impacts in cities and rural areas, but also to see how the impact might differ in Brussels compared to, now we need to think about 200 Amsterdam, will be edgy, but you need to take that into account. You should also see if you put a 200 by 200 grid cell in certain areas that will contain a large part in certain areas sea or ocean, and a large part land, how climate change is affecting changes over land, over sea, it's completely different. So we have the need to further refine that. And there are two big streams to do so. One way is dynamical scaling, where you actually start from that bigger grid, so you have the whole module on global level where temperature changes and so on have been simulated, and you take a smaller area where you increase the spatial resolution, so there you go to a grid cell of 50 by 50 kilometers to say something, and the information from the bigger one is actually used to give the information on the boundary of that grid. And you can do that multiple times till you end up at a resolution of 1 kilometer, even if someone was a bit lower, but you have a grid cell of 1 by 1 kilometers. And that's what you, for example, also see here on this illustration for a run where we use the data for Belgium. So there was already a European module or model run, and then they used that one to serve what is going on in a higher resolution. So you should look at this as, with this model, we know what the temperatures, how they will evolve in each of those grid cells day by day. And that's kind of the boundary that we give the model, the higher resolution one. And from there, it kind of again starts to simulate all those processes, but in way smaller grid boxes, to then see, based on land cover, based on anthropogenic forcing, how that will look like in that smaller resolution. So the big advantage of these models is actually that you always keep on simulating those physical processes. Of course, the finer your resolution, the better you can, represent certain processes. If you have a cell of 200 kilometer by 200 kilometer, and you have one rain process going on, which is in size can be a 1 kilometer by 1 kilometer event, then you cannot simulate that properly if your full grid box is 200 by 200. While if you have a grid cell of 1 kilometer, then that's one process will have a way better representation. In short, it's to give you a bit of an idea what this would mean. The other option is to look into statistical downscaling. Biggest difference is that there you do not simulate every time all those physical processes, and you do not take into account all those equations. You have a morphing methodology that's quite popular, and you have a stochastic weather generator. In the morphing, you start actually from a current weather data file, as you have used in the previous module of Professor Alake. So where you have a 1 year weather data set giving you hour by hour temperature evolutions, weather precipitation amounts, and so on. From those global modules there, you get the information about how temperature will evolve on a monthly basis, how wind speeds might evolve, and you're going to implement that on your current weather file, so on that hourly resolution, by taking certain processes into account mathematically then. So you would, for example, shift your temperature and increase it with 2 degrees if that's the projected change on monthly basis. You might scale it a bit. What you would then, for example, see if you have a heat wave is that you kind of scale as you would physically do, so that you not only increase the upper limit, but it's a longer period of time that it would take into account or would take. You could also shift and scale. So that's really a mathematical change of a current weather file to represent a future condition. The CCVW weather gem is an example of a tool that does that, where you just upload one file and you get projections for the future, unless you know where. Sorry. And then we have the stochastic weather generator, which works a bit similar, but bases itself on a broader set of observations. It's a more statistical model, so it does keep into account certain physical links between, for example, temperature and radiation. It does take into account, so it's a bit more advanced in a morphing methodology. But also there, then you use monthly climate change signals to get a future projection. Meteorlearn has software to do that. Biggest difference is that there you have the observations, and they also try to take into account more the spatial aspects. So they do not start from one single file for one single location. They start from a spatial set of observations to take those into account. The advantage, of course, of the two methodologies on the right is that they are computationally less intense and they're quicker, easier to do. They're a bit less accurate, so depending on what you want to invest, they might or might not be a good option to look at. As they start from current weather, those statistical methods also have the disadvantage that new phenomena cannot be captured. While if you have physical processes, they might occur in your model because you force it with certain conditions, and then something new that we might not be aware of today could happen. If, of course, you start from the world today, and you shift and scale it, you will not get new weather phenomena in those data present, which might not necessarily be a big issue, of course. The advantage also from the dynamical downscaling is the fact that we have that spatial component put in place. With the stochastic weather generator, there are also some possibilities to do so. But then again, it's always a bit of a question that how they use their model, how they also keep relations between the weather at one location and the weather on the other location, so that you could risk to increase one cell with 2 degrees and the other with 3, while the difference wasn't that big. So it's not only the temporal aspect that plays a role and the interaction that play their role, but also the spatial interaction have their components, which is again better represented in the dynamical downscaling, but which comes with a huge computational cost. So it's always a bit of a choice where to look at. If you look into that climate modeling and the dynamical downscaling, then you see over the years all the processes that are represented increased a lot. Here the graph stops at AR4. We're already quite some years further by now, so if you have certain very detailed and refined models today, then you could already have models that have very fine interactions in a city and take that into account. So it's kind of as if you would have CFD simulation, but on a bit of a rougher scale, where you could already say, okay, this building in that street has this anthropogenic heat flux, and take that into account in your model. So that's how we find you could go with these models. You also see on the right-hand side the impact of refining the resolution of your model. here across Europe, but you see a way finer representation of orography, better in a 30 by 30 kilometer grid compared to around 90 by 90. So that's the impact you get and the refinement you get. What can we get out of those models? This is a study that we did to have an estimate of degree days. It's a more simple metric, I would say, that you could use to estimate how the energy use for heating might evolve over time. In this case, you actually look at temperature differences. I think the baseline here was 18 degrees. So you look at if temperatures drop below 18, you kind of calculate the difference between the 18 degrees and your outdoor temperature. And that's actually what is summed up here over a year represented. And there you can get a general idea of, in this case, we would expect under an extreme climate change scenario by the end of the century for Belgium, a 30% reduction, plus minus, for the heating degree days, and that you could somehow already relate, not one-on-one I would say, but with your energy demand for heating in that country. The big advantage here of the fact that we have used a climate model for this, and then we have a spatial resolution of about 3 kilometers here, is that we can see how that evolution differs across the country. So you see cities popping up where we see lower heating demands because we know that it's warmer in those cities. You see here also the impact of some rivers. Liège is popping up. I think here we are having Eindhoven, Lille. So that's the kind of information you get out of it, as well as in our case for Belgium we have higher heating demands in the southern part of the country, related also to the orography in that region compared, for example, in the part of the country. So that's the spatial information you could get out of those type of models. This is on country level. If you would go to finer models, then it could be on city level, which I will show you in a minute. Similar for cooling degree days. So there we kind of wanted to have an estimate of how the energy used for cooling might evolve in Belgium, where we see that on average we expect an increase of 2.4 times. We see that in the present day, actually there's not much of a demand, while in future we see a way more articulated impact across the country. As we have a model at quite a high resolution in those degree days, we could also look at city level, where you see the city of Brussels with forests in the south. We can represent that in the model through the share of the impervious surface area. So we see that in the middle of the city we have almost full sealed surface, while here in the southern area where we have the forest, we have way more vegetation, very low share of impervious surface area. And now you can see what it would mean for the cooling degree days across the city today and in the future. This also highlights that if you would want to look at the impact of a building in the city center of Brussels, and you would want to select a weather data file to assess the energy performance of that building, then it's quite clear that you would need a different one if that building is situated somewhere here. Because in those city, or at least here in this city, you see quite a big difference within the city center and the suburbs, which is of course again related to that where the heat islands playing its role in this. So it's a quite important one. If you look at weather data sets, I think most of the ones you will have used in the previous module will have been weather observations from meteorological stations, which are typically located outside of cities, sometimes at airports, but still outside cities. We typically use those for all buildings across a country, but that can lead to significantly underestimation of certain energy needs depending on where you are located. So that's an important one to take into account. I might go a bit quicker over this one, but this is likely, or telling a bit more. If you have a module and you want to come to a weather file as the ones you have used, then you still need to take some steps, which has to do with it's still a model, so there's still some mistakes in those models, so we do some corrections based on observations. But then you still have sets of 30 years, because what we said in the beginning, you are representing a climate, so that's a longer period of runs, and you do not want to run a building or a city with a simulation of 30 years, because that's a huge amount of data. It takes way too much time depending on the type of simulation. So you also need to reduce that 30-year period into a 1-year weather file, or there might be 2-year files, but you need to reduce the length of the size or the length of the file before you can realistically use it in a simulation in a professional context. In an academic research, you might still have the time to do a 30-year simulation run. If you're working in an architectural office and your client wants to know how the building would perform in another climate condition, then you typically don't have the time to run a 30-year simulation. Let's say that that's even done for one scenario, and you would want to see how a range of scenarios what that impact would be. That's unfeasible, so you need to reduce. There are different ways to reduce such files, and I'll kind of try to summarize what we have here. It comes down to, you can look at typical conditions in a certain climate, or you could look for the most warm conditions or the most cold conditions. If you would look into sizing of your cooling system, then you're more interested in an extreme warm condition to see what is kind of the upper limit, or like 5% upper limit it needs to handle. If you want to have an idea of the energy used, then you typically want to see a bit of the mean situation you would encounter. So that's a bit how it might differ. If you look at thermal comfort, you might be a bit more interested in both, actually, to see what the building in typical conditions gives you as a thermal comfort, as well as if we have a very warm year, an on average warm year, or if we have a year with some heat waves in it, what then your thermal comfort would be. Might be also of interest if we, and that's also what in certain countries it's already the case, if we have blackouts and your cooling systems can just not work anymore because there's simply no electricity, then you could also see in such an extreme condition, how does my building manage the outer situation, and is it still, I wouldn't say healthy, but comfortable, or how uncomfortable could it get in the building, and might there be an option to through increase of thermal mass or some measures like that to improve thermal comfort in extreme warm conditions. If you have those files, and I think that's quite alike with what you've done in the previous model, you can look at how monthly profiles look like, see how, if we here have for temperature a typical flow, how that might look like. If you look at a warmer year, what differences you can see. You have your information for radiation, for relative humidity. That's all information you can take out of those climate models. And the advantage of a climate model, as I said, is spatial, so you can take those files out of it for different locations. And then it might be out of interest to see what is of interest for what you're studying, and that's why I also included this slide again, so where you see, I'm not sure how visible it is here, where the location of an airport is, which we typically see as the source of weather data for the current climate, because there we have observational stations and so on, and that might still have or differ quite a lot with the city center you would like to assess or how you would look at it. A task that has been ongoing in the past 4 or 5 years is one related to the International Energy Agency Annex projects, Annex 80, Resilient Cooling. They had incorporated a weather data task. Why? Because by now, and for sure in the last 8 to 10 years, there has been a lot of work done in the climate change and climate modeling community. A lot of models became available, but there was not much work investigated in how now to use these models into the building domain, I would say. So if as an engineer you wanted to look at a building simulation in a certain future climate scenario, then it was quite hard to know what weather data should I now use. And in this task they really try to bring that together and also to come forward with the first set of weather data files that were created quite consistently, meaning that they used a similar model behind, looked at similar time frames, and could start also to compare across countries and across locations, knowing that the mistakes that might be in their climate data are also consistent across